Hi folks, this is Bass Action, back in action here. We are going to, on this page of notes, start looking at odd and even functions. Before we get into our odd and even functions, we are going to review a little bit of our symmetry test that we did on the first day of the semester. So let's just do a quick review of those symmetry tests. So if you are given a point, and in this case I've given you the 0.57, if you're given that point and you need to reflect it with the given symmetry, let's see where those points would land. So for example, 0.57, the ordered pair 5, 7, we know if we put that in our coordinate plane would be in our first quadrant. Now, if we want to reflect this or have this be symmetric with the y-axis, then what we want to do is we want to move that point so it's in the second quadrant. So the only thing that's going to change in that ordered pair would be the x-coordinate. So our new point would become -5, 7. So that point would be symmetric along the y-axis with the original. Now, if we want our point to be symmetric with respect to origin, this is also often called rotational symmetry. Now we want this point to actually rotate around and be in the third quadrant. So this time we need both the x and the y coordinates to change their signs. So our new point's going to become -5, -7. And lastly, we can look at a point and have it be symmetric with respect to our x-axis, in which case we want to reflect it down. And now we need the y-coordinate to change. So our point would become 5, -7. So just a quick little review on that. Now, those types of symmetry are going to help us understand a little bit better the ideas of even and odd functions. So now, determining even and odd from a graphical approach is actually our easiest approach. And our first one here, when we look at our graph on example 3a, we can see that this graph has a line of symmetry that is the y-axis. When a graph has the y-axis as its line of symmetry, so we call this y-axis symmetry, we say that this function is even. So if we knew the equation for this particular function, we would say that function was even. Now, our next one, we can see that this graph has symmetry around origin. And that phrase around origin is important. So we've got symmetry around origin. And what we would imagine is that there's a point right here at origin. And you can imagine that actually as a pinpoint. So imagine this actually as a pinpoint. And if you could rotate this entire graph around, just rotate this x-axis. We can do this actually in class a little bit more so you can see it a little bit better. But when a graph has this rotational symmetry around origin, we would say that this function is what we call an odd function. So again, if we knew the equation for this particular function, we would say it's odd. Now we can imagine that there are lots of graphs that don't fall under either of these types of symmetry. For example, our example 3c, we can see that it has neither, this has neither y-axis or origin symmetry. And that's okay. Something might have neither y-axis or origin. It doesn't have to have one. However, we would say that this function is neither. Only y-axis symmetry and origin symmetry help us give us an actual even or an odd. Any other type of symmetry or a lack of those symmetries, we will classify it as a neither. Now, as I said, that graphical approach is going to be our easiest approach, but we are also going to need to do this algebraically. So we're going to have some tests here that we're going to do in order to determine whether a function is odd or even. Now, some functions you will actually be able to visualize what they look like. So for example 4a, you can imagine what this quadratic looks like. So you might already have an intuition whether it's going to be odd, even, or neither. But this function right here on example 4b, we don't necessarily have as much intuition what that one's going to look like. So we're going to need to rely on our algebra, and that's okay. So let's just jump into our example 4a. If you're thinking that this is going to turn out to be even because you're imagining a parabola that has been shifted just down on the y-axis, that's a good mental image to have. So let's just keep that in mind. For an even test, what we need to do is we will need to show that f of x, this original function, is actually equal to f of negative x. Now, we already know the f of x function. That's the one that we're given, so we don't need to rewrite that if we don't want. But we do need to actually figure out what is f of negative x. So we're going to follow our steps here. So f of negative x, as we've been practicing for a few days now, says that we need to take a negative x and put it anywhere we see an x. So we're going to have a 5, and we're going to have a negative x quantity squared minus a 7. And then we can clean this up. So f of negative x. Of course, negative x times negative x is going to be a positive x. So this is going to remain 5x squared minus 7. Now we can see that this f of negative x, this 5x squared minus the 7, is the same as our original f of x. Therefore, that's what these 3 little dots mean. Therefore, this function itself is even. Now, if it's even, it's most likely not going to be odd. That doesn't mean that an equation, functions wouldn't be, but that doesn't mean an equation won't be both odd and even sometimes. But we're going to actually show how the odd test works as well. So the odd test, what we're going to do is we are going to show that f of negative x, now notice we've already found that, we need to determine if f of negative x equals a negative f of x. So f of negative x, we already did that one. Let's rewrite it though. F of negative x equals 5x squared minus 7. If you want to write yourself a note. This is just from above, because we already did that work. Now we're going to find negative f of x. You would have done this in your summer packet as well. Negative f of x says we need to take a negative and we need to distribute it to the entire original function. So if I take this negative and I start distributing it, I am going to get negative f of x equals negative 5x squared plus 7. So I can see here clearly that my f of negative x is not equal to my negative f of x. Therefore, this function is not odd. They would have to be the same. So that's our conclusion. So let's do another one. Let's work with one that has some fractions, and then we'll be done with these notes for today. So on our even test, as we said earlier, it's always good to rewrite these. We are going to show or determine, because we're not really sure quite yet what it's going to be, if f of x is equal to f of negative x. So let's figure out f of negative x equals, we need to put a negative x in for that x squared minus 4, and I need to put a negative x in for the x in the denominator. Have to put it in everywhere. Now I'm going to simplify this, and I'm going to end up with my f of negative x. My numerator is going to simplify to an x squared minus 4. My denominator is going to become a negative 2x. So my conclusion, I can clearly see here that my original function f of x is not equal to f of negative x. Therefore, this is not even. And we're done. Let's check and see if our function turns out to be odd. Maybe it will. So we are going to show or determine if f of negative x is equal to a negative f of x. Remember, we have our f of negative x from the previous step, so our f of negative x, let's just rewrite it here for ourselves, is going to be x squared minus 4 over a negative 2x. Now, let's figure out what is our negative f of x. And I will tell you, folks, that the fractions throw people off on this. We need to take this negative right here, and we need to apply it to either the numerator or the denominator. But we do have to choose. So I'm going to write it both ways so you can see what this will look like. I can apply it to the numerator and make it look like this. Negative, and I'm going to have an x squared minus 4 all over a 2x. Or I can write it in another step. Actually, let me simplify this one. I'll have a negative x squared plus a 4 over 2x. Or I can choose to say that I have my x squared minus 4 over a negative 2x. So either one of these are the same. So this expression here is identical to this one. We just chose where we wanted to put our negative. Now, what I want you to notice is that when we distributed the negative to the denominator, what we ended up with was a negative f of x, that this negative f of x equals my f of negative x that I have right there. Now we can see that yes, my negative f of x equals my f of negative x. Therefore, this function is in fact odd. But sometimes you're going to have to do what I did there, and you're going to have to apply that negative to both the numerator and then apply it to the denominator separately and see which one might match.